Hello, this is Mrs. Pullen for AP Statistics, and in this video we're going to go over the Chapter 5 review sheet, and we're going to work on problems 12 through 14 in this video, maybe a couple of others. So you're given a scenario where you're given a two-way table looking at upperclassmen, juniors versus seniors, and the way they typically get to and from school. And so the first problem asks, you select one student at random from this group. What's the probability this student typically takes a bus? And so you would make sure to use proper notation. And so we have 170 students out of 550. And again, the total sample size, it's not a conditional probability. So you would do 170 divided by 550. And when you do that, you get approximately 0.309. Number 13, you select one student from this group at random. If the student says he's a junior, so you have some information, the student is a junior, what's the probability he will walk to school? So the probability he walks, and even though they don't have the word given, it's implied that the condition is they're a junior. You know something about that student. They're not any student, they're just looking at juniors. So this is the information about juniors only. And of those who walk to school, they're 48. So it would be 48 out of 300. And that's 0.16. So choice B, and the other one was choice B as well. Okay. The next part of the problem, number 14, it says, you select one student at random from the group. Which of the following statements is true? Typically, for the events, typically walks to school and being a junior. So part 13, question 13, we can use to help us out with our answer. First of all, we know that the two events, walking to school and being a junior, are not mutually exclusive. And the reason for it is we have 48 students who do both. So they can't be mutually exclusive. This would have to be 0 for that to be a true statement. So that automatically means it can't be A and it can't be C. Next, we have to determine whether or not the two events, walking to school and being a junior, are independent. And we can use the rule, the probability A given B is equal to probability of A if the two events are independent. Now, although you can write it a different way, we already know from 13, we have the information of probability walk given junior. And so as to save some time, why don't we use that? So we know walk given junior is equal to 0.16. So let's see if they're independent by finding out what the probability of A is, in that case, the probability of walking to school. So there are 88 people who walk to school out of a total of 550. And when I enter that in the calculator, I get 0.16. So since the probability of walk given junior is equal to the probability of walk, the two events are independent. So we know it's not mutually exclusive, but in this case, the two events are independent, meaning knowing whether or not someone walks to school has no influence on whether or not they're a junior for this data set. We already did 15 in another video, and we've done 16 on a homework problem. So let's do number 17. We know that probability of A is 0.6 and probability of B is 0.2, and we know probability of A and B is 0.10, and they're asking which of the following statements are true. Well, we know that the two events cannot be mutually exclusive because we notice that the joint probability of both events is 0.10. If they're mutually exclusive, it would be 0. So we know A can't be an answer, and we know B can't be an answer. If they're independent, another way of determining independence is the probability of A times the probability of B would equal to the probability of A and B, that joint probability. That's another way of showing independence. So if I take 0.6 and I multiply it by 0.2, I get 0.12. Well, that's not equal to the 0.10. Therefore, A and B are not independent. So the answer to this problem is D. We know that the events are neither independent nor mutually exclusive. Let's do number 18. Suppose that 4% of the population has a certain disease. A laboratory blood test gives a positive reading for 95% of the people who have the disease and for 5% of the population who do not have the disease. So this sounds like it's one of those tree diagram branching problems. So we're going to start branching. So the probability they have, and let me do that in a different color because that's kind of ugly. Okay. That doesn't go together. So the probability they have a disease is 0.04. So the probability you don't have the disease, I'll use that complement notation, is 0.96. So from that, I know you do this lab test and it reads positive for 95% of the people who really have that disease. So probability positive given disease, and that's equal to 0.95. And so the opposite of that then, so the probability negative that they test negative given the disease has to be the complement of that. So that would be 0.05. And then we're told 5% of the people who don't have the disease also test positive. So the probability positive given that they don't have the disease is 0.05. And so the complement, that would be they test negative given that they don't have the disease. And that's 95%. It would be the complement. So at this point, we want to find the probability of both. And so we're using that general multiplication rule. So you're going to multiply 0.04 times the 0.95. And so I'll get out my calculator. And I get 0.038. And now I take 0.05 times 0.04. And I get 0.002. And now I want to find that joint probability with this other. So I want to do 0.96, the probability they don't have the disease, but they test positive. So 0.96 times 0.05. And then I get 0.048. And one last one, 0.96 times 0.95. And I get 0.912. And if I did it correct, if you take 0.038 plus 0.002 plus 0.048 plus 0.912, it adds to 1. So, unless you've rounded incorrectly, it should add to 1, and it does in this case. So finally, they said, if a person tests positive, what's the probability they have the disease? So this is conditional probability. You know something about that randomly selected person, they tested positive. So here we're using the conditional probability formula that you find in the reference sheet, and that's the joint probability of the two events over the probability of the condition, whatever's in the denominator. So in this case, we're looking the probability of disease and testing positive over the probability of testing positive. And so you're testing positive here and here where my check marks is, and the probability you have the disease and test positive would be where I'm putting the double check mark. So that would be 0.038. And in the denominator would be the 0.038 plus the 0.048. And so I'm just going to enter that quickly in the calculator. And when I do that, I get 0.442. So that's choice C. I hope this video was helpful.